Welcome to the next course of Basics of Mechanical Engineering, Part 3. In this course, we will predominantly focus on thermodynamics and fluids. It will have 60% of the course in the area of thermodynamics and then 40% in the area of fluids. Moment I say thermodynamics, thermo, so that means to say something which is related to temperature, something which is related to heat will be discussed. Dynamics, so with respect to movement, something is changing. So, this course will be more focused towards heat, temperature and its allied. If you look at refrigerator today, it is nothing but a machine which works on the concepts of thermodynamics. The outside temperature is 48 degrees during summer and inside temperature or in a room temperature is around about 24 degrees Celsius. How is this machine trying to bring the difference? Inside a machine, there are several subsystems. Which subsystem does the job such that it throws inside the room a cold air? And of course, there is a conversion of energy from electrical energy to mechanical energy such that the subsystem works and it gives you cold air. So, in this introduction, I have introduced subsystem, system, machine and then I have talked about thermodynamics. You see, in real time, there are lot of applications which are based on this thermodynamics. Friends, let us get into the course. This course will be jointly handled with me, Professor Ramkumar, Department of Mechanical and Design, IIT Kanpur, along with Dr. Amandeep Singh. In this first lecture, we will try to focus on introduction to thermodynamics, overview of laws of thermodynamics. There is a big difference between a law and a concept. Okay. Law are science based, wherein which it has been developed over several iterations and it works wherever you are, it works universal. So, those are called as laws. So, overview of laws of thermodynamics. Then there are different approaches in thermodynamics. One is called as microscopic, the other one is called as macroscopic. Both we will try to see an introduction. Throughout the course, it is only giving you an introduction to all these concepts. Then we will try to look into kinetic theory of gas, history, assumptions and postulates. Then we will try to look into pressure of gas and kinetics interpretation of temperature. We will also see thermodynamic system, what is a closed loop system, what is an open loop system and what are isolated systems. In thermodynamics, there are two major properties which are intrinsic properties and extrinsic properties. We will see that. Then state and path function, thermodynamic energies, work, heat, internal energy as a state of function and finally, at this end of the lecture, we will try to have recap. Friends, when you go through this lecture, you should always look around you and see what are all the machines around you which works on these concepts. The term thermodynamic was invented by William Thomson in the year 1749. It is all about understanding how heat and energy works. How heat and energy works. So, if you overlap your thought process, if you see during this time 1749, there will be front and back lot of industrial revolution would have happened. Small machines would have happened. People would have understood the concept of water. Water, when you heat, it gets into steam. The steam has energy to do or to move certain things. This happened during industrial automation or industrial revolution. So, that is where they talk about heat and energy. It looks at how different types of energy. You can see that there are chemical energy, radiating energy, electrical energy, chemical energy, you have mechanical energy. Suppose let us assume this motion of a car is replaced by a lift, and then that lift is used to move up and down people. So, you have mechanical energy also. So, you can have chemical energy, radiation energy, electrical energy, which gets converted. So, the thermodynamics looks at how different types of energy can be changed from one form to another. When it is getting converted from one form to another, there are three main rules that explain how energy behaves. We will see that. So, here you look at radiation, sun radiates, from this photosynthesis happens, the tree tries to grow. Electric energy, you plug into a socket and you can see induction furnace working, or you can see an induction cooker working, or induction pan working, or microwave working. When you try to talk about chemical energy, it is petroleum. When it is dumped into a car, then it gets activated by a spark plug or by some other thermal. So, there is a combustion happening. Based on the combustion, the heat is converted into mechanical energy and then the car moves, right. So, if you see that all these things, the energy is transformed from one form to the other, and wherein which you try to make use of it. So, now this conversion whatever happens, they say that there are three main rules. What is thermodynamics? It is a branch of chemistry that deals with the movement of energy from one form to another, and that relation between heat and temperature with energy and work is done is nothing but thermodynamics. It tries to bring in a relationship between heat, temperature with energy and work. In the first basic course, we have covered how do you define energy, how do you define work. When you try to take a solid and try to break it, or try to take a liquid in a container, and when you try to look at microscopical, there will always be molecules. These molecules store chemical energy, which can liberate as heat when fuels such as methane, cooking gas or coal undergoes combustion in the presence of air. You have a cylinder, inside a cylinder you will have air mixture of petrol and air getting mixed. It is pushed into a cylinder, and then in the cylinder you have a piston. The piston moves up and down. So, the piston tries to compress, you have a spark plug which sparks and it ignites the air mixture. It now almost like explodes and creates lot of energy. With this energy, the piston moves down. Now, you see chemical energy getting converted into mechanical energy through a process of combustion. In the same way, you can see that in your house also. You have a CUGL or a pressurized gas line coming, or you will have an indent gas through which the gas comes, and then it gets mixed with air, and then you start, there is a combustion happening, and that on top of it you keep a pan, and in a pan you keep water. The water boils. You see how the combustion gets converted into a heat energy. Okay. This release energy can be harnessed to perform mechanical work. You can do it for mechanical, you can do it for electrical. For example, you can try to extract energy. The piston moves back and forth. From there, if I wanted to run a machine, so you can try to do it. So, it is not that mechanical work is converted into energy is the only thing. It can also convert electric energy. Example, diesel generator. Same principle. You have a diesel, you have a combustion. This combustion tries to operate a subsystem. From that subsystem, you try to extract electricity. That electricity is given to rest of your house or rest of your office. So, when there is a power cut, we use DG. So, here it is an example which converts electrical energy and forms a new thing, or it converts into electrical energy through devices like dry cell. For example, if you try to buy a AAA battery and this AAA battery is put inside a camera or put inside a wall clock, it tries to activate the quartz crystal behind and then it starts working. So, this is what they are talking about here. The diverse form of energy are interconnected. Please understand, the diverse form of energies are interconnected, and under specific circumstances they are transformed from one form to another. So, two important words, interconnected and specific circumstances. Under specific circumstances they are confirmed. So, now you are able to see what is thermodynamics. So, thermodynamics is the field that explores and analyzes these energy transformation. So, thermodynamics in a brief is nothing but a science stream that deals with the study of combined effect of heat and work on change in the state of matter confined by the laws of thermodynamics. We will see what are the laws of thermodynamics. Now, are you able to appreciate this definition? Thermodynamics, it is not a definition, it is an understanding, right. Thermodynamics is a science stream that deals with the study of combined effects of heat and work. Heat, temperature, you try to excite something and that gets converted into a mechanical work and then you do something. So, that is heat and work on changes in the state of matter. State of matter can be solid, liquid, gas, confined by the laws of thermodynamics. Okay. So, where do you use this thermodynamics? As I told you, a car uses thermodynamics, a induction furnace uses it, your gas stove which is there uses it, your DG set uses it. So, everywhere you see there is a heat, there is a work. So, there all we use thermodynamics. AC uses thermodynamics, automobile uses thermodynamics, two-wheeler, four-wheeler, rocket uses thermodynamic principles. So, everywhere if you see in a large extent thermodynamics used. You have a centralized cooling in a hospital, follows the thermodynamic laws. You have a centralized cooling in a mall, thermodynamics is followed, right. So, thermodynamics is very important. All engineers should understand the importance and basic laws of thermodynamics such that you do not get too carried away when somebody gives some data in front of you, that is all. So, this course is not in depth into thermodynamics, it goes superficial such that you understand all these small topics with few little calculations towards understanding. So, utilization of thermodynamics is feasibility of a process. If somebody says, I will add A to B, right, without applying heat, then it is not possible. So, if I want to mix two different immiscible liquids, right, and I will try to make a component called as C, A and B mixed together to form a component C. Now, you should understand whether A and B can it mix, and if it has to mix, there has to be a process. So, now when we try to understand thermodynamics, we will try to see whether the process is feasible or not. So, feasibility of a process, it helps to lay down the criteria for predicting the feasibility or spontaneity of a process. That means to say, there is a process which is there, whether this process will work, whether the chemical reactions will happen, whether thermodynamic mixing can happen, right. So, for that thermodynamics plays a very important role. It helps to lay down the criteria for predicting the feasibility or spontaneity of the process. There are some places where ignites and then it progresses. So, that is spontaneity of a process, including a chemical reaction under a given set of condition. So, if something is there, you will be able, if you understand thermodynamics, you can try to understand whether there is the process is feasible or not. For example, I wanted to do cooking, and I wanted to do cooking where the external ambient temperature is -24, and I have a burner where in which the maximum temperature can go only 20 degrees Celsius. I want to boil water. Okay. So, now you can know very clearly that the external temperature is this, the maximum temperature this fellow can go is 20 degrees Celsius. So, this process is not feasible. If I use a one big 10-liter tank of water and then I drop an egg and I wanted to see whether the boiling of the egg will happen, it is not possible. It may be possible, but it is energy inefficient. So, all these things are you will be able to understand and appreciate when you know the utilization of thermodynamics. The extent of a process, it helps to determine the extent to which a process including chemical reaction can proceed before attaining of equilibrium. So, the extent of the process, feasibility, extent can be done, and the last point is going to be the efficiency of the process. The efficiency of the processes study of thermodynamics is based on three generalizations derived from the experimental rules. These generalizations are known as first, second and third law of thermodynamics based on human experiments. So, you can see here there is a heated surface, there is a cold surface, there is a junction in between. Suppose you want to derive the temperature out of this point for a reaction to happen. Then you should know what should be this temperature, what should be this temperature, and what should be the distance, and how is the gradient coming down, and which point I should tap such that I can get my reactions done. So, this can be understood if you understand thermodynamics. So, the utilization of thermodynamics is plenty. It can be used in process industry, product industry, automobile, and then if you want to look at defense sector, everywhere this laws will be used. So, feasibility of a process, extent of the process and efficiency of the process all can be understood when we understand the thermodynamics. And in thermodynamics, we have been repeatedly talking about three. What are the three? Are first, second and third law of thermodynamics based on human experience. Now, let us try to see what are the laws of thermodynamics. I have been talking about 1, 2, 3, but even before that could happen, there is something called as the zeroth law. So, the principles of thermodynamics are summarized in form of 4 thermodynamic laws. So, this is the center which looks at the 4 thermodynamic laws. So, you will have zeroth law, first law, second law and the third law. The zeroth law deals with thermal equilibrium. Two systems, hot, cold, there is a junction. So, there will be an equilibrium reached. So, it provides the means for measuring temperature. So, the zeroth law talks about thermal equilibrium. The first law talks about conservation of energy. It introduces a concept of internal energy. We will see what is internal energy in the due course of time. So, the first law deals with conservation of energy. The second law provides the guidelines on conversion of internal energy of a matter into work. So, first was to provide a means for measuring temperature. Next was to introduce the concept of internal energy. Third one is to understand the change of internal energy into work. So, it introduces the concept of entropy, and the third law defines absolute zero of entropy. The entropy of a pure crystalline substance at absolute zero temperature is 0. So, these are the 4 laws: zeroth law, first law, second law and the third law. First law talks about means of measuring temperature, then it talks about the concept of internal energy, then internal energy conversion into work. So, the last one is talks about the absolute zero of entropy. So, here are some with few examples, we have put the same laws. Let us go one after the other. Zeroth law. if two thermodynamic systems are in equilibrium, that is when Q equal to 0 with a third, then two are in equilibrium with each other. For example, you have a system A, system B, a conductor, and then you have a system C, right. So, Q equal to 0 is the equilibrium. So, when two thermodynamic systems are in equilibrium when Q equal to 0 with the third system called C, then the two are in equilibrium with each other, right. So, you can see here conductor and you have a insulator. So, it is said this one you can see here insulator and then you can say this also there. So, this is insulator and the conductor is in between. So, system A, system B is in equilibrium. The first law talks about the change of internal energy delta U, Q equal to 0, delta U of a system equals to the heat added to the system minus the work done. So, the change of internal energy, for example, you have a surrounding and then you have a piston. Assume that this piston has a weight of itself. So, it slides down and then it tries to compress the air inside. So, here we try to assume it is an ideal gas. So, then a heat is applied. The heat will try to expand the gas and the piston will move up. So, I will repeat, here is a surrounding, the heat is applied to the ideal gas, there is a piston which falls down by its own weight, it falls down, gravity it falls down, it tries to compress. When it is trying to compress, you apply heat, then there is an expansion. So, now this expansion will try to push the piston from here to here, you see there is a work done. So, here whatever is applied is called as W work done. So, delta U is nothing but Q minus W. What is Q? Q is nothing but the heat supplied. Okay. This talks about the first law of thermodynamics. Let us look into the second law of thermodynamics, the entropy S of any natural and spontaneous process either increases or remains constant. So, the heat always flows from a hot body to a cold body. So, here there are two types of processes. One is called as reversible processes, the other one is called as irreversible process. When delta S entropy is equal to 0, then it is a reversible process. When if it is greater than 0, it will be irreversible process. So, you should also understand it, because here if you go back, I was talking to you all the time about process. So, then in the process there are two things, right. So, one, it is to be reversible, irreversible. Irreversible process. Irreversible process means where there is a chemical energy, the chemical reaction happens, it releases energy, then based on that energy you try to do a work. For example, automobile, you fill in petrol, there is a combustion that tries to move the vehicle, it is irreversible. Reversible means I am able to shuttle between hot and cold. So, for example, I make one surface hot, the other surface cold. So, then hot gets transferred to cold and then the cold, when this becomes hot, then it gets transferred. So, reversible is also there. In reversible, the entropy will be always equal to 0. That is why we are talking about the process, irreversible process and reversible process. The third law is the entropy S, you see S. The entropy S of a pure crystal is 0 as the temperature T approaches absolute 0. When T equal to 0 and S equal to 0, it looks like this. See, that means to say it is all occupying a fixed location and it is a pure crystal. So, S of a pure crystal is 0 as the temperature T approaches the absolute 0. When the temperature is away from 0 and the entropy is away from 0, then you see the randomness which is there in the process. Okay. So, these are pure crystals and these are all random. So, they are all moving here and there. So, the system is active. There is an energy which is inside the system. So, knowing the laws, we will now try to see the different approaches. There are two types of approaches which I already told you. One is called as macroscopic approach, the other one is called as microscopical approach. The macroscopical approach is sometimes called as classical thermodynamics. In macroscopic approach, it deals with the overall behavior of a large amount of matter without considering the molecular nature of the substance. So, here to a large extent it tries to average it out. It does not take per molecule heat, vibration, something like that. It tries to take the overall system into existence. The macroscopic approach deals with the overall behavior of a large amount of matter. See, molecular dynamic simulation does take molecular atoms, every atom you can try to add mechanical properties, thermal properties, electrical properties and run a simulation and get it done, right. It tries to tell the behavior in a small cross section area. But when we are looking at mechanical energy systems, there are always massive, big, large. So, we will try to take the overall behavior of a large amount of matter. It focuses on measurable quantities like pressure, volume, temperature and entropy, which is massive. I can measure the pressure. What is pressure? Pressure is nothing but force per unit area. Volume, I can measure the volume. Then temperature, then entropy, right. This approach is practical and forms the basis of classical thermodynamics. So, if somebody talks, I will follow classical theory, classical thermodynamic approach in evaluating the work done. So, that means to say he is taking a larger system and his measurable quantities are going to be force or pressure, then volume, then temperature, then he will also try to do entropy, right. So, the key features, it treats matter as a continuous medium, right. If you try to take atom and atom, between two atoms there is discontinuity. So, here what we do is we say, oh, nothing doing, everything is uniform. So, it treats matter as a continuous medium. It does not require any knowledge on the molecular behavior. Atom vibration, at bond stretching has no matter for me in classical theory. It uses few easily measurable variables. It only takes measurable variables. Interestingly, when you are doing engineering, you should always try to have a measurable parameter as your output. For example, if you try to say the thickness of the hair is 100 micron, I do not have any tool to measure. So, then it is very difficult. You should say if the thickness of the hair is around about 100 micron, which is 0.1 millimeter, I have a vernier to measure it, then yes, you can think of. So, here in the thermodynamics, we always try to use a few easily measurable variables. It is suitable for engineering applications. We always follow classical thermodynamics. If you talk at any automobile engineering, when we talk about anything which is there, when we talk about explosive, RDIX and this and that, so there we go into microscopic approach, but here we always go in a bigger scale. So, the examples under macroscopic approaches, when studying the performance of a steam engine, what is the efficiency of the steam engine, what load it can pull, what amount of coal I dump it in so that I get a steam such that it can pull so many coaches, what is the quantum of coal I should store with me as and when I keep moving a certain distance. So, you are trying to talk about the feasibility of the process, the efficiency of the process. So, when studying the performance of a steam engine, car, rocket, we consider pressure, volume, temperature of steam without worrying about how individual molecules behave. I am sure now you will be able to understand. Heat transfer in a boiler is calculated using macroscopic laws like Fourier's and Newton's law, right. So, by doing so with macroscopic approach, we always try to get the ballpark number. To a large extent, this ballpark number or the thumb rule we follow or first principles we follow, and we try to get the happening what is going on there in engineering systems. So, we are happy with macroscopic approach because we have the parameter to measure pressure, volume and temperature. Now let us look at microscopic approach. Microscopic approaches, you are going to look at very small scales. So then the statistical thermodynamics, it is microscopic approach, is otherwise called as statistical thermodynamics. So the microscopic approach, the behavior of individual molecule or atoms in a system is studied. So here a bulk is studied, here we study in a very small minuscule level individual molecules. It applies principles of statistical mechanics to determine the average behavior of a large number of particles. Inside a dabba, there is one ball. I know when I heat it, what will be the ball's vibration and what will be the influence of one ball on the other ball in terms of force, in terms of temperature transfer, everything. So now what do? I did it with one ball. Now what do? I have 100 balls. So now I average it out. Right? So the statistical mechanism to determine the average behavior of a large number of particles. And heat, what happens is it follows Gaussian distribution. Now in the box whatever I had balls. Now I will have to see how the heat distributes in a Gaussian pattern, what will be the influence of one over the other. Right? Once I apply heat, there is also a possibility, heat is applied, there is also a possibility that here cooling happens. So there is a radiation, there is a diffusion, these phenomena will come. So now what I do is I try to average out the behavior of large number of particles. This approach helps to explain thermodynamic properties at a fundamental level, very small. Today when we are talking about micro, nano mechanisms, we are more interested in statistical thermodynamics. Requires molecular level knowledge, use statistical method to relate the microscopic behavior to a macroscopic property. So I know an atom, now I average it out to a macroscopic property. Macroscopic property are measurable. Vibration is very hard for you to measure. It is visually you cannot measure. So what you do is you try to look into the average property and talk about macroscopic, what will be the pressure distribution. Involves variables like molecular velocity, energy and distribution. I said the ball is nothing but a molecule. Provides deeper insight into the nature of thermodynamic process. However, this is very important, but for an engineer who is interested always to make sure that there is a work which is getting converted for a system to operate. So, he will be interested to make sure the system operates, right. So, there he will always use macroscopic, but if you want to go from fundamental understanding, then you have to go for statistical thermodynamics, which is nothing but microscopic approach. So, there are two types of approaches in thermodynamics. One is macroscopic approach and microscopic approach. So, in microscopic approach, the Maxwell-Boltzmann distribution law describes the distribution of velocities among gas molecules. So, understanding entropy using Boltzmann equation, this requires a understanding at microscopical level, where S is the entropy, K is the Boltzmann constant, and the number of microstates of a system can occupy is omega here. K multiplied with ln omega, you try to get the S. So, now you try to get for a microsystem which can be expanded. So, gas is one of the most important states in thermodynamics. So, let us try to understand little bit more on gas with respect to kinetic theory of gas. So, I just wanted to present one slide on the history. The ancient origins, where the idea that matters is composed of tiny particles, dates back to Greek philosopher Eucrates described atoms as rapidly moving entities bouncing off each other. This was way back in 50 BC. Then the early scientific basis came in 1738 after a long period. The Daniell proposed in hydrodynamics that gas pressure results from molecules in constant motion and related their kinetic energy to temperature, laying the foundation of kinetic theory. So, the kinetic theory was given by Daniell in 1738, right, who gave the relationship between the gas pressure results from molecules in constant motion, the gas pressure. So, that means to say you have a vessel and an atom is moving. So, that is what he says, a gas pressure results from molecules in a constant motion and relates their kinetic energy to temperature. And little advancement happened in 19th century, where James Clerk Maxwell introduced molecular speed distribution, and Ludwig Boltzmann developed statistical mechanisms to explain the probabilistic nature of molecular motion and strengthening the theory's foundation, which happened in the beginning of 19th century. Of late, the modern importance is now central to statistical mechanisms and thermodynamics. The kinetic theory explains the gas behavior and key phenomena like pressure, temperature, diffusion, viscosity and thermal conductivity. Diffusion is very important. So, you can have solid-solid diffusion, solid-liquid diffusion, solid-gas diffusion or gas-gas diffusion. So, all these things have to be understood. Suppose if I wanted to infiltrate in a porous structure, for example, I have a porous flat plate, I am now passing gas to it. This gas has metal vapors. Now, at what pressure I should push this pressurized gas into the porous media such that the metals get occupied in the free porous sites, or when two atoms are held together very strongly, what should be the pressure I should apply such that these fellows slightly deviate and a diffusion phenomena can happen. So, in order to understand that, the modern importance was now central around statistical mechanics than thermodynamics. The kinetic theory explains the gas behavior and the key phenomena like pressure, temperature, diffusion, viscosity and thermal conductivity. For example, viscosity is an important parameter. You can take honey and put a drop of honey on a hot pan, right. So, let us assume you put it on a room temperature and slowly try to heat. You can see the viscosity changing. Take butter, take ghee. So, put butter on a hot pan, it becomes ghee, and you keep on be increasing, the viscosity keeps on be reducing, right. You will have, once the solid becomes a liquid viscous media, this viscous media becomes perfectly liquid, and the next state, if you keep on be heating, it becomes vapor, and you can condense the vapor and do whatever you want. So, viscosity is also a parameter which is important, which has to be understood from the microscopic effect. So, the kinetic molecular theory of gas and the kinetic gas equation were first developed by Bernoulli in 1738. You should understand all these names, because you will see later somewhere Boltzmann constant comes, somewhere Maxwell equation comes, somewhere you will see Bernoulli's equation comes. So, you can connect all these things now. Kinetic molecular theory of gas and kinetic gas equation were first developed by Bernoulli in 1738 to derive the molecular property of a gas molecule on the basis of ideal gas laws and mechanical energy formulae. So, he tried to use this and try to talk about the kinetics of gas. For the study of physics and chemistry, the kinetic theory of gas consists of many postulates or assumptions. Okay. There are a lot of assumptions, postulates are there. In 19th century, the effort of Joule, Coring, Clausius, Boltzmann, Maxwell brought out postulates or assumptions of kinematic theory of gases and kinetic gas equation or formulae on the basis of root mean square, velocity and the momentum of gas molecules. So, they played a very important role. You can say RMS value and the momentum of the gas molecules was studied by them. Molecules in the gaseous state of matter moves generally at a very large speed, molecule in gaseous state. So, liquid you apply heat, it goes to gas, the velocity now they are talking about. The molecules in the gaseous state of matter moves generally at a large speed and force of attraction are not sufficient to bind the molecules in one place. So, in gas state, which is always you convert liquid into a gas. So, in a gaseous state, the molecules travel at a very high speed and the force of attraction are not sufficient such that it sits in one place. Now, what is happening? You have to understand this concept and you will have to give a molecule in a gaseous form to be deposited on top of a flat plate. What is that? That is nothing but coatings. Okay. I should try to now understand the molecule size, the gas pressure and whatever it is, the heat what you apply such that the molecules travels at a speed and then it hits and attracts and stays there. I have to play with the process, right. So, that is what it talks about. At a large speed and force of attraction are not sufficient to bind the molecules in one place. Now, let us start understanding about the molecules. So, solid, liquid and gaseous molecules. Solid molecules. What are solid molecules? Solid molecules are particles are held very closely together and are entirely devoid of any translatory motion. When a specific heat is supplied to a crystalline solid, it takes the form of a vibration motion with the rise of the temperature. Solid, you have a box, take a solid, then you have several atoms there which are sitting here. Now, what do? I start heating. Now, when I start heating, after some point of time you can see the balls vibrating. So, that is what is atoms which are vibrating. So, when a specific heat is supplied to a crystalline solid, it takes the form of vibration motion and it rises the temperature. So, it moves, the temperature moves from the source, it starts moving, right. That is what is vibration motion which rises the temperature. Liquid molecules, with further increase in thermal energy, the vibration motion rises and the molecules break down to transform into liquid state like ice to water. I apply a lot of heat. So, when further increase of thermal energy is done, the vibration motion rises and the molecules break. So, there are atoms. So, now these atoms are there in one position, you apply heat, then it starts vibrating. Now, the vibration, you apply more and more and more heat, this is going to vibrate so much and at one point of time they dissociate and they dissociate, that is what they say, and the molecule breaks down to transform liquid into water. So, now it moves. So, now if you further continue to apply a thermal energy, it is much greater than the force of attraction, then the gaseous state of matter happens. So, when we wanted to give metallized coating or when we have to create fumes or fumes of metal. So, for example, you have a metal, liquid metal, so then you heat it, it becomes a liquid metal, then you further heat it, it becomes vapor. Now, we have a metal vapor, this metal vapor is used for coating. This metal vapor can do many things. When you want to do coatings of cutting tools, they are done by this principle. You can try to apply heat or you can try to sputter, whatever, that is our different stories. Basically, a heat is applied. So, then the gas molecules move randomly and collide with the walls of the container and with themselves, right. This collision are perfectly elastic. Therefore, there occurs a conservation of energy because no loss of kinetic energy or momentum of molecules by this collision. So, we assume that it collides and it does not lose energy, right. That is why it is called as perfectly elastic. So, solid molecules, liquid molecules and gaseous molecules. The take home message of this slide is going to be, therefore, there occurs conservation of energy because of no loss of kinetic energy or momentum of the molecule by this collision. What are the assumptions? If you see, the assumptions are plenty. Gas molecules are continuously random motion in all directions colliding with each other and the walls of the container. Assumption, we assume, right. Maybe it is true, maybe it is staying there itself, we do not know. But when we try to solve a problem, we assume a gas molecule are continuous random motion. So, it is not expected that it will go like this and come back. It can go like this, it can go like this, something. So, that is what is are continuously random motion in all directions which collides with them and which collides with the wall. The actual volume of the individual gas molecules is negligible as compared to that of the volume occupied by a gas. So, now please understand we are talking about gas molecules and gas. The actual volume of individual gas molecules is negligible compared to the total volume occupied by the gas. The third one is the collision between the gas molecules and with the container wall are perfectly elastic, conserving total kinetic energy. That means to say, whenever it tries to hit, it tries to rebound, it does not try to lose energy, it keeps moving. So, collision between the gas molecules and with container walls are perfectly elastic, conserving total kinetic energy. There are no attraction or repulsion force between the gas molecules except during the brief moment of collision. No attraction, no repulsion. But you should understand, when you try to take a molecule, then there are also charges, right? There is no attractive and no repulsive force between the gas molecules except during the brief moment of collision. The motion of gas molecules follow Newton's law of motion, which we have seen in the previous course, especially the second law relating force, mass and acceleration, F equal to ma. The gas in the container reaches a steady state over a period of time where macroscopic properties like pressure and temperature remains a constant, right. So, this is very important. Pressure and temperature remains constant. For example, if you try to see oven where pizza is kept, so when the pizza moves, the temperature increases, but in the oven it is very long. So, there are zones where there is a saturation of temperature happening and there will be cooling happen. So, the gas inside the container reaches a steady state over time where macroscopic properties like pressure and temperature remains always constant. And the last point is, at a given pressure and temperature, the gas exhibits uniform density and the properties throughout the volume. So, at a given temperature and pressure, the gas exhibits uniform density. So, what is density? The molecules divided by the unit area. Uniform densities and the properties throughout its volume. So, the postulates of kinetic theory of gas. A gas consists of a large number of extremely small particles, that is continuous random motion. This is kinetic theory of gases assumption. This is postulates of kinetic theory of gas. The size of the gas particles is negligible compared to the average distance between them. There is no intermolecular attraction or repulsion. The collision between the gas particles and between particles and the container or wall are perfectly elastic, and the average kinetic energy of the gas particles is directly proportional to the absolute temperature of the gas and is the same as the gas at a given temperature. So, these are some of the postulates which is there in the kinetic of gas theory. So, now let us try to look at pressures of an ideal gas. The pressure exerted by a gas results from collision of gas molecules with the walls of the container. The pressure exerted by the gas, right? What is pressure? Pressure is force applied per unit area. According to kinetic theory, the pressure is proportional to both frequency and the force of these molecular collision. Please keep in mind, pressure is proportional to frequency and force of these molecular collisions. Force of molecular collision. An ideal gas is modeled with the following assumption. Gas molecules are point particles with negligible volume. There are no intermolecular forces except between the collision. All collision are perfectly elastic, meaning no energy is lost. So, these are all for ideal gas, because many a times in the problem solving we will say that it is an ideal gas. So, what is an ideal gas? The gas molecules are point particles with negligible volume. So, that is what they say. Gas molecules are point particles with negligible volume, because it is a dot. All the collisions are perfectly elastic, meaning no energy is lost. The pressure P of an ideal gas is connected with volume V and the temperature T and the number of moles N by a ideal gas equation. So, which is nothing but PV equal to nRT, an important formula. The pressure of an ideal gas is connected to volume PV. pressure, volume. That in turn is connected to temperature and N, number of moles, right, N. And what is R? R is the universal gas constant. So, PV equal to nRT. Okay. So, if you want to play with it, then you take P equal to nRTV. So, now you see the relationship of pressure. So, the pressure of an ideal gas is connected to its volume, temperature, the gas constant and number of mole. This is very important equation. The temperature is a measure of the average kinetic energy of a particle in a substance. The kinetic energy rises from the motion of a particle. Vibrations in solids, sliding in liquids and free motion in gas. So, the average kinetic energy per particle is directly proportional to 3/2 K times T, is directly proportional to the absolute temperature T. The relationship is given as K times T. What is K? K is the Boltzmann's constant, which is a constant. So, you have a container, you have these gas molecules. When the heat is applied, you see how randomly it moves. The temperature is a measure of the average kinetic energy of the particles. The kinetic energy arises from the motion. Kinetic energy arises from the motion when it starts vibrating in the solid or sliding. The average kinetic energy per particle is done by 3/2 kT. The lowest theoretical temperature, absolute 0 Kelvin, corresponds to 0 kinetic energy, where molecule motion would be theoretically ceased. So, at absolute 0, there will be no vibration. Everybody will be frozen and it will stand. That is what we say. The lowest theoretical temperature, when no vibration happens, there is a freeze. So, that is called as the absolute 0 K, corresponding to 0 kinetic energy, where molecular motion would theoretically cease. That means no motion will happen. Thermodynamic systems. Thank you very much.